Welcome, one and all, to Chapter 13 of Earth History, Introduction to Earth History for Finlandia University. In this chapter, we will be discussing glaciers and glaciation, something that is of vital importance to the southern areas of Finlandia University, i.e. the Copper Country, the Upper Peninsula of Michigan, and the Midwest of the United States. I'm going to apologize right from the get-go here. I do have a bit of a cough, so if you hear that or if I take pauses to cough, there you go. I apologize. So let us begin. Glaciers. What is a glacier, right? You probably all have a picture of a glacier in your mind, and that picture is most likely accurate. A glacier is a long-lasting, moving mass of snow and ice where accumulation exceeds melting. I.e., a glacier is something that isn't seasonal. Glaciers stay there throughout parts where they grow, accumulation, and parts where they melt, melting, winter, summer sort of thing. The glaciers tend to be very, very large, which allows them to stay. And this largeness of the glacier leads to a very interesting dynamic within the cross-section of the glacier, wherein the lower down on the glacier, with increased pressure, you have increased temperature, things along those lines. The ice on the bottom loses its solid rigidity and actually has a bit of flow to it, has a bit of plasticity to it. Glaciers move not by crumbling necessarily down a mountain, although that's kind of what happens, but it's I guess you could maybe make it akin to the asthenosphere lithosphere conversation we had earlier, but instead of rock, you're dealing with water and ice. Glaciers form by snow, right? This is something that I'm sure we're all aware of. This cartoon here kind of illustrates the process of a snowflake that melts, and then those individual melted snowflakes get pressurized together and compacted into glacial ice. This should look familiar from your sedimentary rock conversations, right? Very similar. That's an important thing to keep inside your head as we move forward. You're going to see a lot of glaciers at high altitudes. We call those high altitude mountainous glaciers alpine glaciers. This is glacial ice mass that accumulates at high altitudes. Glaciers top or cap most mountains because the higher up you get, the colder and wetter it gets. They tend to be constrained to valley channels, meaning the lower parts of these mountains are where the snow and ice naturally accumulates due to gravity, and then the glacier builds up inside these valleys. Glaciers occur on all continents, and it really is dependent on temperature, which is dependent on altitude. You got tall mountains, you can have glaciers on top of them, by definition. Here's a picture, right? And again, look at this glacier. You got a glacier here along the left, a large one sweeping around, but you have some glaciers on the right there too. The glaciers are sitting inside these channels because, right, that's where snow is naturally going to collect. We would not call the snow caps on top of the mountain glaciers because if we go back to our definition, moving mass of snow accumulation exceeds melting. The snow caps are not going away, but they're also not necessarily moving as one piece, whereas this glacier very much you can tell is moving as one piece. Continental glaciers, you sometimes refer to as ice sheets. They're big, right? 50,000 square kilometer area or greater. They're kind of unbounded usually, meaning they flow in whatever direction they want to because they're so big. And these exist basically in Greenland and Antarctica. That's where you would find these continental-sized ice sheets or glaciers. Antarctica essentially is one giant glacier. There are pockets of land that are not covered in snow and ice, but that's just what they are, they're pockets. And Greenland, more or less the same thing. You go to Greenland, you're going there to see the glaciers. Those are the big differences between alpine and continental glaciers. Again, I always like to pause on these so you can, if you want, when you're watching this video, pause it, make sure you can answer all these questions before you continue. That's important, but I'm not going to dive into them over the course of this conversation. We talked about glaciers as where they're located, what they are, right? Big stacks of ice and snow. But the important aspect about a glacier is its movement. That's what separates a glacier from, as I said, an ice cap or a snowpack, something like that. Glaciers move as a coherent unit on a film of water. Again, I guess I'm going to try to make a connection between the asthenosphere and the lithosphere that we talked about earlier. But essentially, the meltwater at the bottom of the glacier is warmed, again, by the pressure, massive pressure of all that ice and snow sitting on top of it. You get some friction along the base of the glacier caused by this melting and this movement, this basal slip, as we call it, that allows the surface water to infiltrate into the bedrock that the glacier is standing on and cause more melting. This movement kind of gives us a plastic-like flow to the glacier, where the center flow tends to be faster than the sides, and the center layers move faster than the deeper layers, giving you sort of a lurching approach to the glacier. The plastic movable part of the glacier is where you can get the deepest concentration of pressure, right? The higher you go in the glacier vertically, the more brittle the glacier becomes, less plastic the glacier becomes, the more that doesn't necessarily want to move. But the bottom part of the glacier is what slides. So the glacier kind of, as I said, lurches forward or falls kind of on top of itself as it travels. And then the center flows faster than the sides, refers to, again, you're getting further away from that pressure, you're touching the sides of the valley, because remember, glaciers, especially alpine glaciers, exist in valleys. These parts here are contacting the rock, being slowed down by the friction of the rock, whereas the inside of the glacier is disconnected from that friction and can then flow at the speed it flows at. The slip-to-flow ratio depends mostly on steepness and thickness of ice. That should sound similar to previous chapters, with the mudslides, the mass wasting, what have you. We tend to call the crack in the brittle upper 40 meters of glacial ice a crevasse. You've seen probably movies where James Bond's in the Arctic, and he's jumping over these giant cracks in the ice. Those are crevasses. They form when the glacier wants to move, but the top part is essentially just ice, and it doesn't want to move, and it breaks as a response to this forced movement from deeper within the glacier. And then within these ice falls, you can within these crevasses and stuff like that, you can have ice fall and what have you, right? Again, the glacier is not uniform in composition. The deeper you go in the glacier, the more the ice wants to melt, but the more it can't due to the pressure, giving you this interesting continuous stack of snow and ice that is simultaneously similar in composition, but different in state of matter. And this is very evidenced by when we watch glaciers move. These pictures here, this cartoon here, demonstrates what they probably could have shown with actual pictures, how a glacier moves. The entire piece appears to move as one, but if you track the individual sections of the glacier, you notice the glacier is, again, the best word I can use now is lurching forward. It is moving as a continuous unit on a macro scale, but as you zoom in, you notice that the inside's moving faster than the outside, and this is kind of ballooning out and massing out as it goes forward. Very interesting concept to grasp. Here we have reference to the brittle and the more plastic parts of the glacier as it moves. Here we have a imagined drill pipe that we have put in the glacier, and the pipe has moved in response to the movement of the glacier, where we have the top part is very brittle, doesn't want to move, hence the pipe is still more or less straight in the top brittle zone because it's basically solid. And then the lower zone is deforming because the ice has so much weight on it, it's no longer solid, acting more like a liquid. It's flowing. And then what happens down here at the bedrock concentration, well, we'll get to that, right? When you get into any of these more deeply, of course, you run into lots and lots of different keywords, lots of different terms used to describe the different areas and different ways in which glaciers behave with the surrounding environment. Zone of accumulation, equilibrium altitude line, zone of ablation, what have you. These terminus moraine, these all describe, in essence, how the mass of glacier interacts with its surroundings. And more or less these things, where if you remember what's going on here, these sentences make sense. What is a tributary? Well, a tributary is, remember, when we talked about what freshwater resources and riverways, a tributary was what fed the larger flow, right? So this tributary glacier is feeding into this larger glacier, hence tributary. If you need be, take a few seconds, pause here. Make sure all these words make sense to you. Try to picture this as if it was a real image, what you would expect. Or, again, think back to, what was that? Live Another Day, Pierce Brosnan Bond movie in Antarctica, right? You have, what does this look like? That looks a lot like my zone of ablation, the crevices that appear. This is due, again, to the glacier moving down the mountain, due, as said previously, to the, where did I put that? Oh, steepness and thickness of the ice, moving down the mountain, causing these breakages because this top brittle zone is a solid and ice doesn't like to bend, but the bottom part is more fluid-like. Again, pause here, make sure you understand this question. I will continue. The cool part about glaciers, as I said before, is they have this balance to them. They have this ability to stay, usually, we'll get to that, right? This ability to consist throughout the years. A glacier doesn't go away in the winter. It doesn't go away in the summer and return in the winter. It's not snowfall. We're dealing with a different monster here. Within the glacier, we have, as said in that previous example, zones of accumulation, zones of ablation, what have you. The zone of accumulation is exactly what it sounds like. It's where the snow accumulates. It's where the altitude is high enough, usually the temperature is cold enough, usually, and you get your piling of snow, the sort of refreshing of the glacier as it travels downhill. Eventually you get to a point where you hit a snow line, where you have a demarcation or a separation between permanent and seasonal snows. And at the very end of the glacier, as it's traveling, is the terminus, or the bottom end or toe of the glacier. That makes sense of this picture, right? The terminus is the end of the glacier. The accumulation zone is the beginning of the glacier. As the zone of accumulation grows, the ice and snow want to fall down the mountain due to gravity, and it slowly pushes the entire mass of the glacier along, extending it, making it larger. And eventually it melts down to meltwater and outwash and what have you. Cool. The interesting part, especially in regards to, again, where I assume you are living, i.e. the Copper Country, the Upper Peninsula of Michigan, the Midwest of the United States, is the way glaciers deal with and affect the area at which they live. In particular, glacial erosion. We talked a bit about this. We talked about erosion a few chapters back. That being said, let's focus in on glacial erosion. Glaciers move huge amounts of sediment and rock material. Glaciers are gigantic by definition. They need to be able to survive the changes in fluxes and weather, right? They got all that mass, got all that power. They're going to move. They're going to pick up rocks, boulders, what have you. When a glacier drives over, say, bedrock or something like that, it cuts what we call striations, or rock material that scrapes along the bottom of a glacier, cuts grooves in the rock that show essentially what the glacier is doing. Because the glacier is still fluid, but it's still ice, right? And if the rock isn't being picked up by the glacier, it instead is going to leave its mark in some way, shape, or form. We can trace glaciers in eons past due to the scratches they've left on the surrounding rock. If you get the opportunity to visit Marquette, Michigan ever, there's a, we'll call it a hill, I can't remember the exact name of it, where the entire top of the hill is covered deep in these striations. And it is very cool to go up there and picture the amount of snow that was on top of this thing at one time to make these cuts. The alpine glaciers, of course, create their own unique and interesting shapes because remember, alpine glaciers are the ones that are in the river valleys, cutting, scouring out chunks of the mountain as they flow down, creating these U-shaped valleys and what have you. Here are examples of the striations that we talked about, right? The glaciers moving, dragging along material, cutting up the rocks. And these cuts here were caused by a glacier that once proceeded over top of these rocks, dragging anything and everything along it. Glaciers have a big impact on the rocks that they're on top of, creating various erosional landforms, tarns, horns, what have you. I think this picture do a better job of explaining what we're talking about here. And they're kind of more or less just different versions of the same thing, this U-shaped valley caused by the glacier. And a lot of mountain ranges start looking this way before erosion gets to it because glaciers glaciers take very big steps. These cool cut out U-shaped lakes being held, hanging valleys, what have you. It's interesting stuff. Here we go. Here's a picture of one of these things. I don't know if it's a horn or a cirque or whatever, but you can picture the glacier here, can't you? This fits in with the concepts we've been talking about. A glacier dug all this out and pushed itself out. Eventually, this particular glacier is receded for XYZ reason, leaving you with this very smooth cut shape. This is drastically different, I should point out, from mass wasting, right? You don't see mud falls and landfalls and creep creating shapes like this, do you? No, you exclusively see glaciers doing this. Hence why we know this was a glacier, due to its shape and other various reasons, such as the striations, what have you. Again, what is the glacier doing? How is it affecting the rock material? Creating these unique cuts, these unique shapes that come from not only the movement of material, but specifically the movement of ice in a certain direction and the picking up of debris and what have you as a result of that. And what I'm trying to say here in short is glaciers are a unique form of erosion that is also going on every single day. You watch a glacier cut into a mountain up in Greenland or what have you, or top of the Rockies, whatever you want to do, you see these things actively working today. Right? That's a very fuzzy picture, but you can see the shape we're talking about here, right? The basin forms as the glacier weathers and erodes away material, cutting you this deep, exposed, what do they call it? These circi? I'm sorry, I should know that better. This deep, exposed, unique-looking environment. That's a picture of the Matterhorn, I believe. Where the Matterhorn gets some of its shape from? Well, you can find those unique U-shaped deposits. Maybe that tells you something, right? We can look down here and we can see these crevices cut out in a shape indicative of that U shape of that almost non-random erosion that you would get from, let's say, mass wasting or landslides, developing the cool look of the Matterhorn. Right? You can climb that if you want to. You do it, not me. I'm not interested. And of course, erosional landforms can give you other things. Fjords, very famous for the Scandinavian countries. Your hanging valleys, which is something we pictured earlier. Right here, a hanging valley. Should off here on the right side of the picture. Glacier was coming down, but the glacier didn't have enough time to dig all the way down the mountain by the time it eroded. I'm sorry, by the time it thawed. So giving you this nice hanging valley, this wonderful waterfall that everyone loves so very much. And again, look at the size and look at the shape of this hole in the mountain range, right? This was a tributary glacier to this large one that ran through. Look at the smoothness and the mirroring of the valley here in this mountain. And that's just a really cool picture. That's really nice. Again, we see evidence of what glaciers do. Therefore, it's safe to say a glacier did this. Glacial deposits. When you walk through the woods, you're going to see what we call glacial drop stones and stuff like that. We're going to get to that here with glacial deposits. When the glacier recedes, what happens to all the stuff that's carrying, right? The striations tend to be formed via the rocks of the glacier dragging, and glaciers obviously pick up a lot of material. Look at all the material that was there that's not, right? This used to be a solid mountain. What has happened with what happens with all that material? Well, we tend to get drift, till, or stratified drift as a result of that. Drift is the term used for all the rock or sediment transported and deposited by a glacier. The broad term, you call it drift. Till would be the material directly deposited by the glacier, and stratified drift is what we refer to as the material that's first carried by the glacier but then moved to a different point. We'll get into till's the interesting thing here. Drift is the stuff the glacier touches, right? Till is the interesting thing because till is material directly deposited by the glacier. Because glaciers move and shove stuff around as well as making their own deposits. Here we can see the last ice age that we had. This is the glacier that was thought to, say, carve out a lot of the unique topography of the Midwest and Canada. And here's the size of it and the thought of directions of glacier movement. Notice down here a terminal moraine line. This is the extent of the glacier. And if we go back to our cartoon showing terminal moraine, we see that is described as the sediment left over at the end of the glacier, right? And interesting enough, what we find, this line is directly linked to sediment that is glacier in origin at these locations, telling us the glacier stopped pushing this far down south and then started to retreat, leaving this moraine, which you can go and visit if you want. Landforms tend to be composed of that till, or that material directly deposited by glacial ice. Erratics are the things I was talking about before, the glacial drop stones. These are boulders that, if you're walking around the woods and you see this giant boulder, it's like, why is that there? A glacier probably deposited it. You need to have a reason to do this stuff. Glaciers can do that. Plus, there's a good chance that glacial striations on it, showing the pulling and the wrecking that particular boulder did to that rock. And of course, moraines, which is what we're talking about here, or mounds or ridges of till, which is that material directly deposited by glacial ice. The end moraine is the deposition at the toe or the end or the foot of the glacier. And within that, you have various levels of moraine dictating certain cool, interesting features of the rock, right? These bumps are moraine. These gyrations, if you will, in the soil were deposited by the glacier, pushing, and then stopping its push at some point, stopping, shoving, bulldozing, if you will, this material. Here's a terminal moraine appearing directly in front of a modern glacier, giving you exactly what we're talking about here. This glacier is shoving, bulldozing, if you will, this material forward, and then when it stops bulldozing and starts receding, that material is still going to be there, giving you something like this. And we can find evidence of these terminal moraines all along this line here. So we know how far the glacier went. Moraines can also be lateral or medial, depending again on where, what the topography of the glacier is going through and how that works, right? Here you have some medial moraines where sediment is being deposited, and some lateral moraines as the glacier moves down the mountain and cuts into the U parts of the U-shaped valley that it's living in. And then drumlins. These are kind of cool. These are elongated hills of till, usually teardrop shaped, that show the direction of the glacial movement. The ice flow flowed in a certain direction along here, creating this unique shape of these hills that were cut out by the glacier. You can notice here the slope, the long part of the hill slope, is the same as the ice flow direction, because the glacier was picking up its material on this side and then depositing its material longer on that side. Drumlins, cool. Other various landforms that you can get from the stratified drift. The stratified drift, as I said before, is not what the glacier left. It's what happened to the stuff that the glacier left. Here you can have outwash, valley trains, eskers, kettle, what have you. I'll let you pause on here if you want, but an image works best to explain this concept. Here we can see, again, remember that long part showing the motion of the glacier. Here we can see the various plains, moraines, lake sediments, kettle ponds produced by the forward expansion and the retreat of the glacier. Notice this top picture, this glacier is already in retreat, right? Because you have a moraine built up from the bulldozing of the glacier right here. And the melt off from that glacier has created a stream valley that already cut through the moraine. As it continues to move backwards and backwards and backwards, further types of deposit are built because of the mass of this glacier pushing, backpedaling back, if you will, melting, not say backpedaling, but melting back, creating all these unique individual shapes. Right? During a pause in its retreat, glacier deposit a recessional moraine, sediment transported by the meltwash forms the outwash pond beyond the glacial terminus, etc., etc., etc. Why do we have two moraines here? Because the thing was retreating, it stopped retreating, depositing this material, could continue retreating, what have you. And again, this all relies on what the glacier wants to do and what the surrounding topography of the glacier lets it do. But if we find evidence of these individual geologic features in nature, that tells us something about where the glacier was and how the glacier acted. So let's talk about the Pleistocene glaciation. This was a time when alpine glaciers descended into low-lying valleys and continental glaciers advanced at high latitudes. There have been 6 major glaciations in the last billion years. Essentially, you could say ice ages, if you will, if you know that term better. The most recent glaciation started about 2 million some odd years ago, and we called it the Pleistocene glaciation. The high latitude temperatures, high latitude being the North and South Pole sides places, dropped by as much as 15 degrees Celsius, allowing an expansion of these glaciers. Here we have a graph showing the temperature and carbon dioxide over the past 400,000 years, showing this massive jumps in temperature, but in general, staying very low, right? That's cold. 15 degrees less than the average temperature, which is this dotted line here. That's not average carbon dioxide, it's average temperature. Right? Actually, no, I correct myself. That is supposed to be, those two are related. My bad. Look how cold it was. The blue line. Actually, no, I was right. I should read this graph more. That line is for temperature, is not related to carbon dioxide. Point is, the two are connected anyways, right? You can very much see the trend of carbon dioxide and temperature flowing with each other. It was cold back in the day. Glaciers formed, right? What could cause an ice age? What causes glaciation? Well, volcanic ash layers can be found in ice cores. The volcanic ash layer is found in old ice Volcanic ash probably comes from volcanoes. Lots of volcanology, lots of volcanic activity occurring around the time of this Pleistocene glaciation. More glacial sediment grains, etc. And we have certain cycles in the Earth's orbital character that can play a big factor in this, because temperature, of course, is also related to the sun, right? There's a certain eccentricity to the variation of the elliptical shape of the Earth at about 100,000 year period that can bring us further or closer to the sun. This variation does have a very big impact on the temperatures that we have, along the course of the tilt and precession, gradual wobble, and extra variations of the Earth itself and the directness of the sunlight that hits it. Here we have an example of what we're talking about here. So, sun, that's where basically all the heat energy that affects the top of the Earth comes from. The inside of the Earth has some degree of heat, geothermal heat, but the sun's the major player. The closer you get to the sun, the more of the sun's energy hits the Earth, the hotter it is, right? Present orbit out here in blue, 100,000 year orbital shift inside in red. Cap it with that, the precession path as you go around, and the changes in tilt by degrees all make it so that the sun's energy can have a greater or lesser impact on the Earth, thereby causing or being a contributing factor to ice ages. It's all, it all plays a factor. It really all does. What are the effects of the Pleistocene Glacier? Well, we've talked about those already. The Great Lakes, for example, one major effect. That image I showed earlier showed how far the glacier went. That was the last glacier. It was a Pleistocene glaciation event that essentially carved out a lot of North America shape. It also affected a lot of Scandinavia, Russia, what have you, but right, we're talking about America. Lost plains, ice mass causing sea levels to drop, isostatic rebounding of continents. These are all features and topics that we've covered in previous chapters that, again, are all coming back to play a role. Ice is heavy. Ice sitting on a continent is heavier than no ice sitting on a continent. That causes the continent to dip down more. That affects the tectonics activity of the region, affects the ice. Obviously, if it's going to grow, it needs water from someplace. It's going to soak up seawater, what have you, affecting the total amount of seawater, affecting the amount of continents that are available, et cetera, et cetera, et cetera. Lots of interplay within this concept. You can extend all the conversations I just had into a theory called Snowball Earth. Snowball Earth is the idea that the Earth has been completely frozen over in the past, possibly twice. Glaciers can extend, as we saw previously, down to whether it be Pennsylvania, Indiana, Kentucky area, right? Well, how far can those glaciers extend? What if we clump up the continents closer to the poles via plate tectonics? Can the entire Earth be covered in glaciers? That's a theory, right? One example of this is interesting is tillite. Tillite occurs on almost every continent in the same time frame. Tillite should sound familiar to you, right? Because we talked about, where are you at? Till. Till is material deposited directly by glaciers. What do you think tillite is? Tillite is a rock made of till, right? And since it occurs basically on every continent around the same time frame and lies mostly on top of limestone beds, which we talked about limestone before, right? Maybe this goes to show that continents throughout the world have actually been covered in glaciers before, essentially giving you a frozen Hoth-like planet. This is contentious. I'm not saying this happened, but it is something that is still discussed in the geologic community as a possible explanation for the Earth in the past. The Earth, in no way, shape, or form, has been uniform in its composition and its look, right? When we talk about geologic time, you go back, to the Jurassic. You're not just going to walk out of the time machine pod and breathe the air the same and feel the temperature the same and have the chemical composition of the atmosphere be the same. A lot of different stuff has happened, possibly including Levi-Ann Hoth. Recently, however, we haven't been having increases of glaciation. We're having decreases in glaciation. The Earth's glaciers have been disappearing. As of summer 2003, about 10% of glacial ice in the Alps has melted away. 10% is a lot. That's 1/10. That's a lot of glacier. That's gone. Glacier National Park has shrank by about 2/3 since 1850. That's a whole lot of ice, right? The North Pole regions have been warming faster than anywhere else, and there's a lot of ice and glaciers up there. Well, not really glaciers up there. There's a lot of ice pack up there. In Greenland, the continental ice shelf has thinned by about 1 meter a year since 1993. 1993, that was a long time ago, right? That's 27 years ago now. So you're talking over 20 meters of ice have been lost off of Greenland since that time. And Antarctica itself has shrunk by about 13,000 square kilometers in 1974. That's a lot of loss of ice. And keep in mind here, this isn't, well, it's gone, but it's come back. This is total loss. It hasn't come back. It hasn't bounced back every single year per these calculations. Right? Here's a fantastic example. A picture of the massive glacier in Glacier National Park, Montana in 1932, and then that same place in 1988. There is no glacier. This glacier didn't bounce back, it's just gone. How does this play in? Well, we'll get to that in future chapters here, but glaciers are more than just ice. Glaciers are more than just snow. Glaciers are more than just meaningless compact. Glaciers represent a cooling factor for the Earth. Glaciers, probably more so than that, are carbon holders. They hold CO2 and other various greenhouse gases that in their interworkings. If a glacier melts, it lets off more than just water. So these are all interesting things to take into account. And if this much ice is gone in Montana, this much ice is gone in all the other parts of the world where it used to be as well. And that's a big change in a little amount of time, right? The Earth doesn't like to move very fast. The eons and the glaciation events last hundreds of thousands of years. This is 50 years between these two pictures. So, yep, that's all I have for this conversation. I'd like to thank you for stopping by. If you have any comments, please feel free to leave them down below. I or another student can get to them. Thank you for watching Chapter 13 for Finlandia University. Take care.